Okay, I hope I'm audible to all students who are attending this lecture of Mathematical Methods for Economics, Part 2. Okay, we intend to start with a new topic within this course, which is called as integration. We intend to start with a new topic within this course called as integration. Okay, formally this is chapter 10 of the book I prefer to follow for the Mathematical Methods in Economics Part 2 course, which is Sater and Hammer. Okay, this is the book I prefer to follow for my lectures on integration, the 4th edition of this book. Okay, so let's start with the lectures on integration. Now, the first topic we are interested in looking at is how to find the area under the curve. So all students can write this heading, area under the curves. This is the first subtopic within integration. So we are interested in looking at method for finding the area, method for finding the area below the curve y equal to f of x and above the x-axis from x equal to a to x equal to b. So we are interested in finding the area below the curve y equal to f of x and above the x-axis from x equal to a to x equal to b. So a diagram is going to help in understanding what is the area we are actually aiming to find out. So all of you can see the diagram. We have the x-axis, we have the y-axis. Suppose this is my function y equal to f of x. Okay, this is my function y equal to f of x. I am interested in finding the area above the x-axis below the curve from x equal to a to x equal to b. So this is the area we intend to find out. Okay, so step one, find an arbitrary function, capital F, that is continuous, on the interval a to b, okay, such that if you differentiate capital F of x, you get small f of x. I repeat, if you differentiate capital F of x, you get small f of x. Okay, for all x belonging to the open interval a2. So guys, what is step one telling us? Step one is telling us that for the function small f of x, we have to find the antiderivative capital F of x. Now, capital F of x is called the antiderivative of small f of x. So all students can write it here. Capital F of x is the antiderivative. Now guys, antiderivative is also called as the integral. Capital F of x is the antiderivative of small f of x such that if you differentiate capital F of x, you get small f of x. So step 1 is telling us that we need to find the arbitrary function capital F, which is continuous on the closed interval a to b, such that if you differentiate capital F of x, you get small f of x. So guys, how will I find capital F of x? So I can say capital F of x is equal to integral as x goes on from a to b f of x dx. Since we have said that capital F of x is the integral of small f of x, or integral also means antiderivative, I can say that capital F of x is equal to integral from a to b small f of x dx. Okay, so now we know how to find the area, guys. So step 2, what is the required area? Required area is given by, now guys, when I integrate f of x, I get capital F of x. When I integrate small f of x, I get capital F of x. And capital F of x, I will run from a to b. So what do we get? Capital F of b minus capital F of a. So the required area is nothing but capital F of b minus capital F of a. So I am revising this concept again with all students. Okay. What are we looking at? This is the application of integration which students have also done in high school mathematics. We are looking at how to find the area under the curve above the x-axis from x equal to a to x equal to b. In the diagram, you can clearly see I have drawn the curve y equal to f of x. We are interested in finding the area above the x-axis below the curve f of x from x equal to a to x equal to b. That means, guys, we want to find out this shaded area. So how will I find this shaded area? We are given the function small f of x. The objective is to find the arbitrary function capital F, where capital F is the antiderivative of small f, such that when you differentiate capital F of x, you get small f of x. Other way of saying it is that f capital F of x is nothing but the integral of small f of x dx as x goes on from a to b. Okay, as x goes on from a to b. So now when I integrate small f of x, I get capital F of x. Now capital F of x, we have to run from a to b. So this will be capital F of b minus capital F of a. So hoping that all students have understood this particular concept and have no doubts. Okay, so now let's do some practice questions based on this particular concept which we have learned. So our heading now is practice questions. Based on area under the curves. Practice question based on the area under the curves. Okay, so let's look at the first question. Calculate the area under the parabola. Calculate the area under the parabola f of x equal to x square over the interval 0 to 1. So we need to calculate the area under the parabola from my course on mathematical methods for economics part 1. In my lectures on coordinate geometry, all of you can recall that this is nothing but the equation of a parabola with the vertex at 0, 0. Okay, so if I draw the diagram for this particular function, the diagram is going to somewhat look like this. So all students can see on their screen, this is x-axis, this is y-axis. If I plot f of x equal to x square, it is going to look like this. Okay, but we want to find the area as x goes on from 0 to 1. Now all of us know, guys, when x is 1, what is y? 1 ka square, which is also 1. So the objective is what? The objective is to find the area under the parabola and above the x-axis. That means we need to find out this area. This is the area we need to find out. So that means, guys, how will I find the area? So I can say, what will my required area be? Required area will be integral as x goes on from 0 to 1 f of x dx. This is how we find the area. This is integral as x goes on from 0 to 1 f of x is equal to x square times dx. All of us know, guys, what is the integration of x square? Now all students can recall from high school mathematics. Integral of x to the power n dx is x to the power n plus 1 upon n plus 1 plus the constant of integration. Although I will be doing this in my lectures on indefinite integrals, but just a recall for all students, integral x to the power n dx is x to the power n plus 1 upon n plus 1 plus the constant of integration c. Now x square ka integral is x cube by 3. We don't need the constant here because anyways it's definite integral. So x cube by 3 we will run from 0 to 1. So this is going to be 1 ka cube by 3. Okay. So this is going to be 1 ka cube divided by 3 minus 0 ka cube divided by 3, which is 1 by 3, which is my required area. This is my required area. So we directly have to apply the formula for finding the area under the curve and above the x-axis from one point to the other point. We have directly applied the formula. We know how to integrate x cube, x square. In general, x to the power n ka integral is this. So x square ka integral will be x cube by 3. Okay. And x cube by 3, I will run from 0 to 1. That means first I put 1. Then I put 0, I subtract, I get the answer as 1 by 3, which is my required area. Okay, let's now look at question 2. Okay, find the area. Find the area capital A under the straight line. Under the straight line given by f of x equal to cx plus d over the interval a to b, where c and d are constants, such that my function f of x is greater than equal to 0. So let's read the question again. Objective is to find the area under the straight line. So can we quickly plot the straight line? If I quickly draw the diagram for all students. So again, we have x-axis, we have y equal to f of x here. How do I plot the line cx plus d? We are given that c and d are constants. Both of them are positive because we are given that f of x is greater than or equal to 0. That means if I put x as 0, I get my f of x as b. Okay. f of x is equal to cx plus d. When x is 0, f of x is equal to d. And d is positive because we are given that the function is positive, upward sloping. So this is my function f of x equal to cx plus d. We now need to find the area of this from x equal to a to x equal to b. So this is the required area we need to find out. So how will we find the required area, guys? Directly apply the formula which we have learned. Required area is integral as x goes on from a to b, f of x dx, which is integral from a to b. Now f of x is cx plus d times dx. Now guys, cx ka integral is cx square by 2 and d ka integral is dx, and I need to run this from a to b. Remember guys, integration of a constant d is nothing but d times x because we are integrating it with respect to x. Okay, now in this I can first put b. So cb square by 2 plus db minus, now I can put a, so ca square by 2 plus d. And if I continue to solve this on the right hand side of the screen, let's see what do we get. So I can write cb square by a plus db minus ca square by, this is, let me correct it, this is cb square by 2 plus db minus ca square by 2 minus dA. So this I can write as c by 2 times b square minus a square, okay, plus d times b minus a plus d times b minus a. This is the required area. Okay, so I hope all students have understood this particular practice question. We were given the straight line. We had to find the area over the interval. We directly apply the formula. We solve for the integral. We put in the integral the expression b minus, we put in the expression, we put in the integral the expression a. We solve for this. We get the required a. Okay, now all students can write the next case, which is as follows. Okay, so our heading now is finding the area below the curve, or I can say finding the area above the curve, finding the area above the curve y equal to f of x and below the x-axis. And below the x-axis from x equal to a to x equal to b. So guys, this is the second case. If all of you can recall, the first case which we had done was finding the area below the curve and above the x-axis. Now we are doing finding the area above the curve and below the x-axis. That means now we are in the negative quadrant. So this means I can say that that is f of x has negative values. This case simply means that f of x has negative values in the interval a to b. Now how will we find the area? So again I can say step 1. So suppose I draw a diagram for all students first before writing the steps. Now guys, the diagram is as follows. X-axis, this is my y-axis, okay, and you can see now that I am drawing a curve which is as follows. You can clearly see So this is my curve y equal to f of x. This is my curve y equal to f of x. And suppose this is my value x equal to a. This is my value x equal to b. So now we have to find the area above the curve and below the x-axis from x equal to a to x equal to b. So how will we find this area? So I can say that again our step one is the same as which was before. So we can say that find an arbitrary function. Find an arbitrary function capital F that is continuous. That is continuous on the interval a to b such that capital F dash x equals small f of x for all x belonging to a to b. That is, we can say that we need to find capital F of x, which is integral small f of x dx as x goes on from a to b. And then guys, step 2, what will the required area be? The required area A will now be f of b minus f of a, but with a negative sign. The required area will now be f of b minus f of a with a negative sign. Why? Because now my area is in the negative quadrant. You can clearly see that in the shade area A, you can see that y is negative. So I once again repeat, the objective is to now find the area above the curve and below the x-axis. Everything will remain the same. You will find the function capital F of x, which is nothing but integral small f of x dx as x goes on from a to b. But now your required area will be f of b minus f of a with a negative sign. Okay, so now let's do a practice question based on this particular case. Let's look at the practice question. So the question is as follows. Compute the area. Compute the area between the x-axis and the graph of f of x equal to e to the power x by 3 minus 3 over the interval 0 to ln3, 0 to 3 ln3. So we need to compute the area between the x-axis and the graph of f of x over the interval 0 to 3 ln3. So guys, first of all, we can plot the graph. Let's plot a rough sketch of e to the power x by 3 minus 1. So clearly, if you look at the function f of x equal to e to the power x by 3 minus 1, let us see what happens when x is 0. So when x is 0, then f of 0 will be e to the power 0 minus 3, which is 1 minus 3, which is minus 2. That means you can see that the graph is starting from the negative y-axis, minus 2. Then guys, we need to check whether it's upward sloping or downward sloping. Now please recall from the MME-1 course, how do we check whether the graph is upward or downward sloping? Find the first derivative f dash x. E to the power x by 3 into x by 3 ka derivative is 1 upon 3. which is positive. Therefore, I can say f of x is upward sloping. Then guys, how do we check whether the curve is concave or convex? That means we need to now comment on the curvature. Is it concave or convex? So for that, we find the double derivative f double dash x. If I differentiate f dash x again, 1 upon 3 e to the power x by 3 into 1 upon 3, which is 1 upon 9 e to the power. Okay, so I can write it like this. This is 1 upon 9 e to the power x by 3. So I can write it here. Okay, I can write it as 1 upon 3 f double dash x is 1 upon 9 e to the power x by 3, which is positive. So I can say, therefore, the graph is convex to the origin. So guys, the graph is upward sloping and convex. So my graph will be like this. Okay, this is now going to be the graph. Okay, so I have to find which area as, okay guys, another thing, let's find out this point. What is this point? So how will we find this point? Put y as 0. So putting y equal to f of x as 0, putting y equal to f of x as 0, what do we get? 0 is equal to e to the power x by 3 minus 3, which implies 3 is equal to e to the power x by 3, which implies if I take log on both sides, ln 3 is equal to ln e to the power x by 3. Now all of us know guys, ln e is equal to 1, so I can say ln 3 is equal to x by 3. So what is my x? My x is nothing but 3 ln 3. Okay, my x is nothing but 3 ln 3. Okay, so this point comes out as 3 ln 3. So we now need to find the area as x goes on from 0 to 3 ln 3. That means guys, this is the required area we need to find out. So I am revising with all students still here. We were given this function. We need to find the area over the interval 0 to 3 ln 3. How do we find the area? First of all, we plot the function. When x is 0, you can see y is minus 2. So my function starts from minus 2. First order derivative is positive. That means graph is upward sloping. Second order derivative is also positive. That means graph is convex. How do I find the point at which the graph cuts the x-axis? Put y as 0. Solve for x. You get x as 3 ln 3. We need to find the area from 0 to 3 ln 3 above the curve and below the x-axis. Now, how will we find the area? If I erase this particular part, we have just done the formula, guys, for finding the area. So let's now find the required area. Okay, so let's apply the formula which we have done. So I can say required area is given by integral from 0 to 3 ln 3 small f of x dx, which is integral from 0 to 3 ln 3 small f of x is e to the power x by 3 minus 3 times dx. Let's integrate this. Now e to the power, all students recall, e to the power kx ka integral in general is, e to the power kx ka integral is e to the power kx divided by k plus c. Although we will be doing this in our rules for indefinite integrals, but I am revising it again. E to the power kx ka integral is e to the power kx divided by k plus c. So e to the power x by 3 ka integral is e to the power x by 3 divided by 1 upon 3 minus 3 ka integral is 3x. So this will be, as x goes on from 0 to 3 ln 3. So guys, this will be 3 e to the power x by 3 minus 3x as x goes on from 0 to 3 ln 3. Now all we have to do is plug in the values. So I am erasing the right hand side of the screen and solving this up further. Let's see what do we get. So erasing all this off, we can write it as, first I put 3 e to the power 3 ln 3 divided by 3 minus 3 times 3 ln 3 minus, now I put 0. 3 e to the power 0 minus 3 into 0 is 0. And guys, since we are finding the area below the x-axis, it will have a minus sign outside. Because you all students must have written in your registers that when we are finding the area below the x-axis and above the graph, then f of b minus f of a will have a negative sign outside. So this is going to be minus of 3 e to the power, this 3 and this 3 cancel out, ln 3 minus 9 ln 3, okay, minus 3 e to the power 0 is 3. So this will be minus of 3. Now guys, e to the power ln 3 is nothing but 3 only. E to the power ln 3 is 3 from properties of natural logs. Minus 9 ln 3 minus 3. This comes out as minus 3 3s are 9, 9 minus 9 ln 3 minus 3, which comes out as 9 minus 3 is 6, so 6 minus 9 ln 3, or I can write as 9 ln 3 minus 6. If I open up the brackets, the minus sign, I get 9 ln 3 minus 6. This is the required area. So hoping that all students have understood this question. First of all, you need to plot the graph. You need to draw a rough sketch. We have drawn the rough sketch. We have identified that we need to find the area below the x-axis and above the graph. We solve it the usual way, but in the end, I take a minus sign outside. In the end, I take a minus sign outside because we are finding the area below the x-axis. So everything else remains the same. I continue to take minus outside. When I solve, I get the answer as 9 ln 3 minus 6, which is the required area for this question. Okay, so guys, this is where I intend to stop in this particular lecture. The objective of this lecture was to cover with all students the first concept of integration, which was to find the area under the curve, either above the x-axis and below the curve, or below the x-axis and above the curve. Okay, so I hope all students have enjoyed this lecture. Any doubt, you can unmute your mics and ask, or call up, or you can mail me your doubts at divineschoolofeconomics@gmail.com. So this is where I stop in this lecture.